In this video, I will show you how can you draw enantiomers or diastereomers for a compound. So first of all, how can we draw enantiomers? If you have a compound which has one chiral center, then you can draw an enantiomer for this compound by either just drawing the mirror image of the compound without changing the dashes and wedges. So this is one option. Or you can draw the compound as it is, but instead of having a wedged OH, just draw it as a dashed OH. And this will be enough to draw an enantiomer for a compound. Remember that those two are actually the same. So if you try to determine the absolute configuration for these two compounds, you will notice that this is S and this is also S. Of course, after inverting the configuration. If your compound has two chiral centers, then again, either draw the mirror image and don't change dashes and wedges, or keep the compound as it is, and then the wedged Cl is now a dashed Cl, and a dashed Br is a wedged Br. If your compound is drawn in the Fisher projection form, then it will be just enough to switch those horizontal groups to draw the enantiomer. So Br will be on the left side, CH3 on the right side, and don't change the other ones. Even if your compound has two chiral centers, then you can do the same thing. So invert the first chiral center and then invert the second chiral center. And so we inverted those two and those two, and this is how you draw an enantiomer for a compound. Now, if the compound has more than two chiral centers, the same method can be applied, whether it has dashes and wedges, or if it has if it is a Fisher projection. How can we draw in diastereomers for a compound? To draw diastereomers, you have to invert one chiral center or more, but don't change all of them. So if your compound has two chiral centers only, you can change only one chiral center. If your compound has more than two chiral centers, you can change one and two, but not three chiral centers. So for example, in this case here, I can draw a diastereomer by changing the wedged Cl into a dashed Cl and keeping the Br as it is. Or I can change the other one, which is wedged Cl will stay as a wedged Cl, and then we will have a wedged Br. So you can change one in this case, but not all of them, because if you change all of them, those will be enantiomers. If you have a Fisher projection, again, you can change the top one or the bottom one. So if I change the top one, then the other one should stay as it is, OH on the right side, CH3H, or I can invert the bottom chiral center while keeping the first one as it is. So OH here will be on this side, and then CH3 here, and this is H. So this is how we draw a diastereomer for a compound, whether it's drawn in the dash wedged form or in the Fisher projection form. But the question is, how many stereoisomers can we draw for a certain compound? This is usually can be given by this equation, which is 2 to the power n. So whenever you are asked to determine the total number of stereoisomers for a compound, first of all, you have to determine n, which is the number of chiral centers that exist in this compound, and then you use this equation, which is 2 to the power n, to determine the total number of stereoisomers. If the compound has only one chiral center, then it is going to only have two isomers, which is 2 to the power n equal 2, and this is R or S. So for example, if I have a compound which has only one chiral center, then I can draw this compound in two forms only, either in this form or in this form. The first one will have R absolute configuration. The second one will have S absolute configuration. Now, no matter how many changes you do, it's going to be at the end one of these. So if I, let's say, someone draw the molecule in this way, well, in this case, this is again S. Someone might draw the molecule in this way. This is again R. So no matter how many changes you do, at the end you will end up either with this form or this form. So if you have only one chiral center, your compound may have only two isomers. If your compound has two chiral centers, then 2 square will be equal to 4, and which means that you can draw the molecule in 4 forms. So RR, SS, RS, or the other one will be SR. So for example, let's say I have a compound which has a BR here and a CL here. This is one form. The other form is both dashes. And I can also invert the CL, keeping the BR as it is, or invert the BR and keeping the CL as it is. And these are the 4 different ways by which you can draw a compound which has 2 chiral centers. Any other thing will lead you to one of these 4 stereoisomers. Similarly, if your compound has 3 chiral centers, there are 8 different combinations to draw this compound. However, sometimes we have to pay attention that if the compound has 2 similar chiral centers, then the number of stereoisomers will be reduced by 1, and that's why the equation will be 2 to the power n minus 1. For example, in this case here, so if you are given this compound, pay attention that those 2 chiral centers are the same. What do I mean the same? The first chiral center has OH, the bottom one has OH. This one has H, this one has H, this one has a CH3, this one has a CH3. So those are 2 similar chiral centers. They are holding the same groups. And that's why once we try to draw all the different options, we will notice that actually 2 of these options are the same. So if I try to assign the absolute configuration now, so the first molecule starting with this one, which is here, this is 1, 2, 3, so this is R, it's S, 1, 2, 3, and this is SS. The second molecule will be RR. So those are 2 different stereoisomers, and those are enantiomers to each other. Now, if you look at those 2 compounds here, if you assign the absolute configuration for the top chiral center, this is going to be S, and this is going to be R. On the other side, this is going to be R, and this is going to be S. However, pay attention, since those 2 chiral centers are holding the same groups, those 2 compounds are actually considered as one compound. Why? Because this compound has 1 chiral center with S absolute configuration, and this has 1 S absolute configuration. This is R and this is R. So those 2 are actually considered as one compound, and then we have 1 here and 1 here. So that's why the total number of stereoisomers is 3 instead of being 4, and that's why the equation here is 2 to the power n minus 1, which is 2 square minus 1, so 4 minus 1 equals to 3. But again, this discussion is only valid if you have 2 similar chiral centers, because it's only in this case when you have when you consider those 2 are the same. However, if let's say I have a BR here and BR here, then this is going to be completely different. Why? Because the chiral center which has OH is S, and in the other compound it's R. The chiral center which has BR is R, and the second compound is S, so those are opposite. So you only use this modified equation or this approach if your chiral centers are the same. If not, then you just use the 2 to the power n equation, which is the first one.